Hello everyone, thanks for joining in. I'm Karthik Devasigamni, Chief Architect at Noon, the social learning platform. This talk is about how we built a real-time analytics system to track our classroom quality for all our teachers and students. We started our journey on Druid back in December of last year. This has actually opened up a lot of possibilities for us on the data side. In this talk, we will be discussing the problems that we have faced with our online classroom. And before I introduce the problem space, I would like to talk about who we are. What does a live classroom experience look like? How do we measure the quality of experience in a live classroom? And then move into the solutioning part, where we'll discuss more about how we built our real-time classroom monitoring powered by Druid. I'll also share some of the key challenges that we faced, the lessons that we, and also the business impact that we were able to create with this solution. Without much further ado, let's jump right in. Noon was founded in 2013 with the sole aim of helping students prepare for tests. But over the years, we have, after multiple pivots, we've landed on social learning. And our mission has always been the same, to radically change the way people learn. We have realized through a lot of experiments that the real problem in learning is actually not about content or anything. It's more about the boredom in the learning process itself. We aim to solve this problem by making learning more fun, and that we wish to accomplish by making learning more social. By social, what I mean is peer-to-peer learning, where you don't just learn from your teachers, but you also learn from your peers. So we are currently serving more than 5 markets, primarily in the Middle East and South Asia region. We have about 10 million plus students who have tried out our app. Currently, we have more than 1 million monthly active users, and the users who are active on our app, they tend to spend more than 50 minutes studying on one of their active days. So that's a little bit about who we are. So jumping into the live online classroom, right? So the live online classroom is the one feature where students spend most of their time on the Noon app. A majority of the time spent, right, goes in learning from the teacher today by the students in this classroom setting. The classroom setting that we have at Noon is very similar to what you would find on Microsoft Teams or Zoom, right? There's video, audio, chat, and a whiteboard. And these are the 4 major tools that the teacher uses to actually deliver their lecture. Apart from this, the other key component of the classroom is actually breakouts. So the teacher can, at any point, pop up a question on the student's screen, and then the students will actually go into a small breakout with their peers, and they'll get an opportunity to discuss the question amongst themselves, and then come back with the right answer and present it to the larger audience in the classroom. So that's where the social learning actually happens. And we have seen that for some of the popular sessions, that we've seen around 10K students attending those sessions. So moving on, what are the major problems that our students and teachers face? The biggest one is actually the audio issues, right? Where the students are not able to hear the teachers, and this can happen for a variety of reasons, which we'll come to in a bit. But when this happens, the teacher's attention gets distracted. The students start bombarding the teacher with a lot of messages on the chat. Once the teacher sees it from a lot of students, then the teacher's attention goes into that, and then the whole class is actually disrupted. And when the whole class is disrupted, it actually creates a it creates a problem for all the students, not just the ones who are actually facing the issue, right? So based on our experience, most of the times when we see that the voice is broken issues being brought out, it's either a problem on the teacher's network, or a problem with the microphone that the teacher is using, or an issue on the students' internet quality. We've also seen occasions where because this is VoIP, using the BRTC, we do see some ISPs, policies coming into play as well. The other key area of challenge inside the live classroom is around the whiteboard, right? The whiteboard, if students are not able to follow what the teachers got on the screen, then that's another major area of concern for students. And again, they start complaining on chat, and then the teacher again gets distracted. So when such an incident happens, our support teams come into picture. The teacher actually reports those issues. The support team gets notified, and they'll notify the engineers, and then everybody's scrambling around to find out what is going on, right? As we started ramping up, as we started gaining more users, we started noticing a surge in these kind of issues being reported. And once once it got to a certain point, we took a step back and said, why don't we actually start measuring our real quality of experience of this classroom, right? So this is the standard Wikipedia definition of quality of experience. There are two parts to measuring the quality of experience, right? One is the quantitative part, where you're able to really measure and attribute things, and the other one is largely around the perception, right? So in this talk, we'll talk more about the quantitative things, like in the case of the audio quality and the whiteboard. It's largely around the network parameters and the audio quality parameters. So before we get into those, what those parameters are, right? A very, very brief overview of what our classroom looks like. It actually, our online classroom uses a third-party voice as a service called Agora. So they provide us with voice and real-time messaging SDKs, and these SDKs are embedded into the client applications. So when a teacher decides to actually start a session, they connect to the Agora servers, and then that that audio stream is actually broadcasted to everyone on the receiving or student side. So when it came to monitoring the classroom and determining the quality of experience for all our students, we sat down, identified what it actually means, and how do we actually go about measuring it, right? So the parameters that we came up with on the metric side were largely around uplink quality, downlink quality of the network, both on the student side as well as on the teacher side. And then packet loss that actually happens over the wire, and then the audio quality itself, whether it's excellent, poor, or it's broken and things like that. Then we also capture the mic status, whether the microphone is actually on, off, the audio levels, jitter buffer delay, and then the frozen frame rates of the audio packets, and then the uplink and downlink bit rates. In the case of whiteboard, we capture something called as a drift, which actually measures the difference in the number of strokes between what the teacher has drawn on his side versus what the student sees on his side, right? In terms of dimensions, we want to look at this across a wide variety of dimensions. I've just captured a limited set here. Geographic, user, based on sessions, ISPs, the network types, and their the kind of devices they use and things like that, right? In terms of aggregation, what we want to compute, we are interested in finding out the quantiles, count, distinct count, average, and standard deviations. So once we got all of our quality parameters defined, we then started looking at what would be the system attributes that we would want when we design such a system, right? One thing became very, very clear for us, that we want it to be real time. The reason why it needs to be real time is that when the teacher actually reports an issue about a problem in the live classroom that's actually happening, we don't want our support team to go back and say, hey, there's a batch process that will run and we'll get all the data after 4 hours or 6 hours or 12 hours. That's just not possible. So we wanted, real-time ingestion, and that was one of the primary requirements for the system. The second one is around horizontal scalability, because as we started adding more, teachers and more students, more sessions started happening, and this means, more data gets generated, and we want to be able to scale horizontally. And as the number of students, increases, number of sessions increases, the dimensions, on which we want to compute certain metrics and aggregations on, they start increasing. So we want the system to be able to handle high cardinality data as well. Not to mention, sub-second query latency, because when you're on a call trying to help answer these questions, you don't want to be waiting for your query to take like a minute or so. So you want sub-second latency. We want fast aggregation on large volumes of data, and then the ability to be able to zoom in and zoom out. I'll show you an example of what I mean by zoom in and zoom out. Basically, we want to have a bird's eye view at a country level as to what is going on, and then drill down into what happened across all the sessions inside the country, and then what happened to all the students within a particular session, and then being able to drill down to a particular student at a certain point of time, right? So we want this ability to zoom in and zoom out, and of course, the system has to be available all the time, so that when an issue is reported, we can actually go back, look at it, and then revert back with what is actually going on there. So when we were looking around for to build this, right, one thing that really stood out when we compared a lot of solutions out there was Druid. The reason why Druid stood out was very obviously because Druid was one thing, was one system that actually supported real-time ingestion out of the box from Kafka. Yes, the spec files tend to get very lengthy, but it was pretty easy to get started if your data is actually in Kafka. The second thing was that Druid is actually distributed in nature, and that allowed us to actually scale things horizontally. You could add more data nodes, more query nodes, and then you've got your, you can actually expand your cluster as more data comes in. The next important thing that we found about Druid was the data sketches, right, which was able to actually handle high cardinality dimensions for us, because for us, as the user base starts growing, computing aggregations on user dimension became very, very important. The next thing was around low latency querying, which Druid is already popular for. The other part that caught our attention was the ability to actually give both exact aggregation and also approximate aggregation. We had use cases for both. Like in some cases, we were okay with knowing the approximate values, and in some cases, we wanted to know the exact one. So Druid had the ability to do both. The next thing was around the data size itself. One of the things that we found really attractive in Druid was the ability to actually summarize or aggregate data at ingestion time, which is called as roll-ups, something that we'll talk about in the subsequent slides as well. This helped us, reduce the size of our data set as well. And when we look at Druid, because it was distributed, there was redundancy built at all levels. Like if you have your real-time task that is actually running, those tasks actually had, you can configure replication for those tasks. The master nodes, you can set up HA for those master nodes. The data, you could actually put it in deep storage, and that is again, is durable as well. So the fault tolerance in Druid is actually built at multiple levels that takes care of the availability problems for us. So moving into the the data collection part, right? Once you've figured out that we're going to use Druid, the next step for us was to figure out how we are actually going to collect these data and push it to the server. So like I mentioned in one of the earlier slides, we have those SDKs on both the teacher side as well as on the student side. These SDKs, have a callback. They get a callback every 2 seconds with all the network and audio quality parameters. So these are provided by WebRTC itself. So what we do is we collect these statistics every 2 seconds, and once and it's impossible for us to send this to the server every 2 seconds. So what we did was we buffered them for either 60-second interval or a terminal event, which could be student exiting the classroom or other such terminal events, and then flush them to the server. The server component was fairly straightforward. It's just a simple microservice that actually gets all of these requests, checks for, does some sanity checks on those payloads, and if everything passes, then it just dumps it into a Kafka topic. The stats collection for Whiteboard is a little bit different from what we had to do for the audio side of things. So for the Whiteboard, the way our Whiteboard works is when the teacher actually draws a stroke, that the XY coordinates on that particular stroke is captured as an array and is broadcasted to a real-time messaging channel, from where all the student devices actually start subscribing from. So in the table here, you can see that if you have to write A, you have to make 3 strokes, 2 slanting lines, a forward slash and a backward slash, and then the horizontal line, right? So what we do is when a stroke is actually getting generated on the teacher side, we generate 2 things along with that. We generate a unique message ID, and these message IDs are actually monotonously increasing sequence numbers. And along with that, we also send a checksum, and the checksum is basically the sum of all the message IDs up until that point. So the table actually gives you an illustration of what the checksum looks like. So this information is sent to, it's broadcasted on a certain channel, and all the students subscribe to it. They receive the strokes, and then they start rendering it. Now, we also have a service called Noon Classroom Interceptor that intercepts all these messages, picks up all the message IDs and checks them, and then periodically sends heartbeats to all these student devices via PubSub. And the student devices, as soon as they get this heartbeat, they look at the message ID and then the latest checksum, and they compare it with the checksum that they have last received from the teacher side, and also the checksum that they have computed on their. If these 2 checksums matches, that means you are seeing exactly what's there on the teacher side. If there is a mismatch, that means you're off. And using simple arithmetic, you can actually compute how many strokes you've actually missed. So this information is gathered again every 10 seconds, buffered on the client side, and then flushed out back to the server, to the same microservice. The service receives it, does some sanity checks, and dumps it back into a Kafka topic. So once the data is all collected in Kafka, the next step for us was to just ingest it into Druid. And this is where we started noticing a pattern. Basically, what we were doing with this ingestion stage was picking up data from Kafka, and because there was some sort of batching there, we had to unpack the events, split them, and send out the individual events, and then just massage the data into a format that Druid can easily understand. So we started pushing, writing Flink topologies to do this, and then on the real-time ingester on the Druid side, wherever there was rollup enabled, we, the spec would actually have that, and also we did some conditional transformations on the ingestion side itself, so that we don't have to do them on the query side. One of the things that we're looking forward to using is the lag-based autoscaler, because a lot of the time, we see uneven distribution of traffic, like a lot of hits, a lot of sessions happening at the same time, and then there is a lag in the ingestion process. So that is something that we are looking forward to actually using. So once we started noticing this pattern of receive the data, parse it, and then massage it and push it into Druid, we said we can actually make this easy by some sort of automation. So what we did was we built a very simple DSL in JSON that captures the essence of what this transformation logic should look like. Like for example, here you can see here in the JSON path section, there is a JSON part that says what is the value of that particular dimension and how to actually extract it. And this information is used by the Flink transformers. And then the other information inside this DSL file is largely around the metric names, the dimension names, and then what kind of aggregate function that we want to run on those metrics. So once we capture all of this information in a single file, what we did was we used this file to generate our Flink topologies. We also use this to generate the spec files that will finally get ingested into ingested into Druid via Jenkins job. So we've written Jenkins jobs that would actually take these spec files, take these DSL config files, convert them into spec files that can be submitted to Druid for ingestion. So this allowed us to scale our ingestion process and push a lot more metrics into the system in a very easy, seamless way. When it came to schema design, it was very, very obvious that you have to start with your use case. So always start with your use case. Understand deeply what is it that you are actually trying to measure, and once you got that right, just identify the dimensions and metrics. And once you pick your metrics, what kind of aggregations do you want to run? Do you want it to be approximate or do you want it to be exact? The next thing in the schema design that you have to pay attention to is the query granularity. If you think you need something on a daily basis, right, aggregate at a daily basis, then make sure that you have your rollups set to day. If you need something at a second level, then configure it to a second level, but that comes at a cost, right? You will be storing a lot more raw data there. Partition, again, in our case, because everything is real time, we used dynamic hashing, and we had configured our max rows to 5 MB for the secondary partition. Deep storage, we used S3, and data retention, depending on different use cases, different data sources had different data retention in our case. So with that, I just wanted to show you how our dashboards look like, right? The zoom in and zoom out that I was actually talking to you guys about. So you could actually see a zoomed out view, which is at a country level, what is going on for the network quality and then the audio quality, right? These are quantiles computed using data sketch extensions. And then once you have the country level audio and network quality, you can actually zoom into what is going on within each session for a particular country, right? So here we're looking at the network and audio quality for all the sessions for one country. And then from there, you can actually pick up a particular session and zoom in on that and see what is the overall engagement and quality metrics for a particular session. And once you got that, then you can further drill down to a student level view to understand what is actually happening to each of those individual students inside a particular classroom. And once you got the overview of all the students, you can actually zoom in to a particular student and then find out what exactly happened at a second level granularity, as you can see from this dashboard here. So this allowed us to take a bird's eye view of where we are in terms of our classroom quality, and then be able to sort of zoom in and go into a particular session and identify the students who are actually having issues and do something about it if we can to address that problem. So in terms of our cluster, the way we had set up our cluster, there's no surprise there. We got our master node, data node, and query nodes, and we used external Zookeeper, MySQL, and S3 for deep storage. The key thing that I wanted to call out here is we used tiering for our data nodes. The reason why we had to use tiering for our data nodes is that some of the jobs that we had actually used rollups, and there were high volume of traffic coming in, and we saw that those nodes that actually those data nodes that were actually ingesting and doing rollups required a lot more memory than the other ones. So what we did was we created high memory tiers and started allocating tasks to the ones that needed rollups. We would assign those tasks to those nodes. In terms of monitoring the health of the cluster, we use Datadog for everything else at Noon. So there was a Datadog Druid plugin that made it very easy. Just install it on the servers, and we were able to pull out all the metrics with ease. By default, it gave us all the system resources like CPU, memory, JVM memory, and also disk I/O, and then the load and other things out of the box. The ones that we were primarily interested in were were the ingestion lag, the number of segments, and query time. The ingestion lag always tells us, how far behind we are in terms of, getting data into Druid. The number of segments played a key role because we were actually ingesting data. If the number of segments due to late arrival of messages, we did see some, jump in number of segments from time to time, and we'll talk about how we addressed that problem in a subsequent slide. And we would also monitor the latency on the query side. In terms of some numbers, just to give you a sense, we have more than 15 dimensions and 50 plus metrics on our Druid cluster at the moment, and we process more than 105 million events per day, and we have about 2 billion rows with an average row size of 1 KB over a period of 14 days. The number of segments that we have, we actively monitor that and try to keep it in that sweet range between 4K to 5K. Again, that is the reason why that sweet range is depending on our cluster capacity and our size. The P90 latency for most of our, for all the across all the queries that we run is still less than 1 second, and there's some crazy queries that we actually run. Most of the times, I've seen our ops, run queries across a broader time range, whereas what they need is actually a very small subset of that data. So putting everything together, this is what the overall picture looks like. The apps have all the instrumentation logic. They push out all the metrics that we want to Noongate service, which collects all these metrics and pushes it into Kafka topic. From there, we run our Flink jobs that primarily just takes those events, reads a configuration file, runs the transformation logic, basically extracting all the fields from the JSON payload and populating all the dimensions and metrics into a flat JSON key value pair, and then pushes it to a Kafka topic. Then we have our Jenkins job that actually take this DSL configuration file and then calls the Druid ingestion spec generator APIs, which will generate the spec file for you, takes those spec files, submits it to Druid, and runs the ingester task. And once the data starts flowing into Druid, we have our dashboard that I just showed you, which is used by our both our engineering as well as our support organizations to go and look at what is going on inside the classroom. So the tool that we use for visualization is actually the older version of Imply Pivot. It's called Turnino, the open source version of it. That's what we use internally right now. So what is the business impact of this, right? The biggest impact for us was the ability to quickly identify problems. Our turnaround time started improving dramatically because once an issue was reported, we never had to look at multiple places to know what is going on. We just had one dashboard, could just go there and then see what is going on, and then be able to explain whether the problem is on the teacher side or whether it's a problem on the student, or is it a problem because majority of the students are on 4G network, or we are easily able to troubleshoot and identify and say where the problem was. The second thing that this really helped us was we were able to validate the fixes that we were putting in to improve the quality of the live classroom. The moment you deploy some changes, we can actually go back to the dashboard and then see if it is actually improving the quality of the classroom, right? The next thing was that previously, with the older, in the world before we built this tool, everybody had to go through logs and databases to understand what was going on. But now this has become a self-serve tool, and you don't need developers to tell you what is going on. You could just, as a support engineer or ops engineer, you could just look at it yourself and then understand what's going on there, right? This also improved the trust and transparency, between the ops team and the developers. The most significant one for us was, because the classroom quality was so important, it was reported as one of the major issues when we did our student NPS. And our student NPS score started, moving in the right direction with all the improvements that we had actually done. So in terms of challenges and key lessons, right? One of the things that we learned was that, use rollups, because most of the times what people want is they want aggregates and they don't want it at a second level data for everything. So if you think there is a scope for you to actually use rollup, go for it. It's your best friend. It improves not just on storage, but also, when you're actually querying data, you have to parse very less amount of data. The next thing that we found, very useful was doing transformation at ingestion time rather than doing it at query time. Doing something at ingestion time, you just do it once. But if you're doing it at query time, then everybody who's running the same query is actually doing it. So it just makes sense to actually push that logic all the way up into the ingestion phase of things, right? The next thing was, was understanding the trade-offs, right? What kind of metrics you want, and whether it needs to be exact or approximate, and exploit the data sketches and hyperlog algos that come out of the box with Druid. The next major challenge that we had was late arrival of messages. Because our ingestion was all real time, we had a lot of cases where there are messages that would actually arrive, say 2 hours or 3 hours or 4 hours after the actual event had happened. And what this did was, it was actually creating segments, additional segments. And when we initially started our journey on Druid, one of the challenges that we faced was keeping the size of the segments within a certain number, because once the segments got fragmented too much, it created all kind of problems when we were actually querying the data. So what we did was we scheduled compaction periodically. So the workaround for us was we scheduled compaction multiple times throughout the day to make sure that the late arrival messages, the segments that it creates, are not left as is, and we run periodic compactions to keep the number of segments healthy. The next thing that we learned was, the query performance itself, right? It's largely dependent on how you've actually designed your data model. So make sure you spend enough time thinking about your data model upfront, because that is going to help you with optimizing your, making your queries more performant. The other big thing that we learned was, when we started our journey on Druid, right, it took us 2 months to actually get to a stable state. And once we got to that state, by stable state, what I mean is, we would run jobs, and then we would find that, we needed to tier things up a little bit on the data nodes, because certain jobs needed more memory, and then in some cases the roll-ups. So there are a lot of these learnings, and it took us about 2 months. But once we set everything up, right, and things started stabilizing, we never had to really go back and touch that. I think in the last, since Feb of this year, right, was the last time that we actually had to, make changes on the cluster. Since then, the cluster has been just running very smoothly. So the key thing for us was, yes, there's a little bit of learning curve, but once you cross that, right, it just works. The last thing that I want to highlight was, the community support, right? When we were, setting up our cluster and trying things out, that we found the Druid user group to be super helpful, right? Don't be shy if you run into issues, throw your questions there. There are a lot of kind souls in that group who take the time to actually respond. So I really appreciate the help that we got from the Druid users mailing list. That helped us, get our cluster up and running and make it more stable. So that brings us to the end of this session, and I just want to take a moment to thank everyone in my team who has actually contributed to this, and also to the Druid users mailing list for answering all our questions. So that's it from my side, and happy to take any questions.
Thanks, Karthik. Great presentation. Really lots of useful information about working with Druid in a streaming context with Kafka. So we do have one question in the chat. Did you use any tooling in order to work out what memory tuning you had to do to get to that stable state? Like, how did you think through things like heap sizes and stuff like that?
Yeah, so so it was more trial and error. We didn't use any specific tool. So basically, what happened was we were seeing that certain tasks were actually getting killed. And when we went into the Druid logs and looked at it, they were all failing because of out of memory. And we noticed that it was not failing because of out of memory on the JVM heap size, but it was on the max direct memory buffer size. So it was more a trial and error, and then we started, monitoring these task level, JVM metrics more closely, and that's how we identified. So it was not, we didn't use any specific tool, but it was more the logs. We used to monitor the logs like hogs for those 2 months.
Got it. Okay. Thanks. Any other questions for Karthik? Going once, going twice. No, I think we're all set. So thanks so much, Karthik, for your fabulous presentation. And everybody enjoy the rest of the conference. Thank you.
Thanks, guys.